A very good afternoon to all of you. I am Ashmita Das, a PMRF research scholar from IIT Guwahati. Today I am going to present some assignment questions for the subjects PT 13 Bioelectrochemistry week 3. Now moving to the questions. So here comes the first question. Read the following three statements carefully. The activity of an ion in a very dilute solution close to infinity and therefore can be expressed in terms of the ion concentration. So that means if a ion if we can find a very dilute solution, the activity of the ion is close to infinity and therefore it can be estimated by the terms of ion concentration. The second statement is, however, the ion concentration is not equal to the ion activity for a solution having higher concentration. So this sentence is exactly the opposite of the sentence where we can say if the ion solution is very diluted, we can measure the ion activity based on its concentration. But when the solution has a very high concentration of ion, the ion concentration is not equal to its ion activity. The third statement is, in order to use the Nernst equation in such cases, the experimental measurement must be conducted to obtain the true activity of the ion. So based on these three statements, there are four options given. First option is 1 and 2 are true while 3 is false. The second option is all the three statements are true, 1, 2, 3. The third statement is statement 2 and 3 are true while statement 1 is false. And option 4 is all the statements are false. So now we can say for the answer, these statements all pertain to concept the ion activity in a solution. So number first, in a very dilute solution, the activity of ion can be considered close to infinity, meaning that it essentially behaves as if its the concentration were very high. This allows us to simplify calculations by expressing the activity in terms of concentration. So in a very dilute solution, the activity of ion is close to infinity. Means its concentration, that means is essentially behave that its concentration were very high. This allows us to simplify the calculation by expressing the activity in terms of concentration. Now moving to the next question. However, this simplification breaks down in solution with very high concentration. The ion activity can deviate significantly from its concentration due to factors such as ion-ion interaction or solvent effect. So that means when the solution have a very high concentration, the ion activity can deviate because from its concentration various factors such as ion-ion interaction or solvent effects. Now the third, to accurately use the Nernst equation in such cases where the ion activity may differ from its concentration, experimental measurements are necessary to determine the true activity of the ion in the solution. To accurately measure the Nernst equation for these cases, the ion activity is different from its concentration. Experimental measurements are necessary to determine the true activity of the ion in the solution. This measurement help correct for deviation from ideal behavior and ensure the accuracy of calculations involving the Nernst equation. Now moving to the question number 2. In a galvanic cell, reduction occurs at anode, cathode, depends on the electrode used, none of the above. So basically, if we consider this is the reaction chamber, so there are two electrodes and this is, so they are half merged, so we can say the, if this is the positive, if it is the anode and this is the cathode, and if they are connected externally, this is the anode where oxidation takes place, and here because of that, suppose it is made of zinc. So what happened, the solutions started, the electrode started to deteriorate and produce Zn2 plus ion, which dissolve in the solution, whereas the produced electrons are transferred from anode to cathode through a external circuit. After reaching to the cathodes, the electrons are combined with the at the same time copper from the copper electrodes. Coppers are also dissociated in the solution, but after reaching the electrode, these Cu2 plus 2 ions receive the electrons and produce copper, which is deposited on the electrode. So after a certain of time, we can see the anode is started to degrade, whereas the cathode become thicker. So in a cell, we can use, in a galvanic cell, reduction occurs at cathode. So we can very easily, in a very quick explanation, it can be explained. The anode is where oxidation takes place. It is the electrode where electrons are produced during a spontaneous redox reaction. The half reaction at the anode involves the loss of electron, whereas in the case of cathode is the reduction take place, the electrode where electrons are consumed during the spontaneous redox reaction. The half reactions at the cathode involves the gain of the electron. So in summary, we can say reduction occurs at the anode, oxidation occurs at the anode, reduction occurs at the cathode. So it can be say in a very, we can say in this way. So OA become RC, or we can using the terminology, remember OARC, OAR. So basically, oxidation occurs at anode and reduction occurs at cathode. So now moving to the, so based on this question, we can say that in a galvanic cell, reduction occurs at cathode. Now moving to the question number 3. Delta G equals to NFE, where delta G is the change in free energy, N is the number of moles, F is Faraday's constant, and what is the E? There are 4 options: electron charge, current, voltage, and charge density. In our equation, del G is equal to NFE. The del G represents the change in free energy. N represents the number of moles of electron transferred in the reaction. F represents the Faraday's constant. So if we write this equation, the Gibbs free energy usually describes the spontaneity of the reaction, which depends on the number of moles, Faraday's constant, and the potential and the voltage or the electromotive force. So E here represent the voltage, more precisely the cell potential or cell potential of electromotive force. It is the potential difference between the two electrodes of an electrochemical cell, which measured in volts. So this equation can be, we can say in detail. So first the equation I'll explain in more detail. So delta G is equal to NEF. This so we can say, so based on the question, delta G is equal to NFE, where delta G is the change in free energy, N is the number of moles, and F is the Faraday's constant, A equals to what? So there are four options. The correct option is C, voltage. Now moving to the next question. A reaction is spontaneous if delta G is dash and E is dash. So as I say, from the Gibbs free equation, the common equation who determine the spontaneity of the reaction is del G equals to minus N F and E. Okay. So if we say this terminology, I suppose consider this entire is a constant K X. Okay, just a minute. This is the value of N and F as a constant. So del G is dependence on the sign of the E. Okay, so when I get the del G sign of the E, this is dependent on the of the E. So basically the del G is positive when that means del G is negative. Just a minute, I'll get back. I'll help you to understand more in this. So basically, as I say here on the top, the del G equals to minus E. So if E into K, so as I said, if the E value is positive, the entire del G value is negative or less than 0. Suppose del G is negative, so it becomes minus E into K. So then the del G become positive. So based on the del G value, there are three states. The three we can describe three things. So first, del G is less than 0, that means the reaction is spontaneous. If del G equals to 0, that means reaction is in equilibrium. Or if del G greater than 0, that means the reaction non-spontaneous. Non-spontaneous. So in this case, the del G should be less than 0. So for that we need del G equals to minus NEF. So if these two terms become constant, so it should be positive, then del G becomes negative. So reaction is spontaneous if del G is positive. So these two questions are the option C and option D is for cut here itself, and E is sorry for the mistakes. So the first two options is cut there itself. The reaction del G is positive because del G should be negative. So there are four options C and D, and E should be positive. So the correct answer is option C. Now we can move to the next question. When a nerve cell is at rest, dash and dash cannot pass across the membrane of action, but the dash can flow across the membrane from the cell interior to the exterior. As a result, a dash potential exists across the action membrane. So there are four options. K ion means potassium ion, Cl ion means chlorine ion, and Na ion means sodium ion. As a result, dash a potential can be positive. So second option is the sodium ion and chlorine ion cannot pass, but potassium ion can flow, and as a result positive potential exists. Next time, sodium ion and potassium ion cannot pass, but chlorine ion pass and a negative potential exists. The fourth option is sodium ion and chloride ion cannot pass, potassium ion can flow, and there is a negative potential is exists. So the correct answer is when nerve cell is at rest, sodium ion and potassium ion cannot pass. Sorry, not sodium ion, it's a chlorine ion. This is the chlorine ion cannot pass across the membrane, but the potassium ion can flow across the membrane from cell interior to the exterior. As a result, negative potential existed across the membrane ions. Now, the resulting resting membrane potential. So this particular situation is known as the resting membrane potential. It refers to the electrical potential differences across the axon membrane of a neuron when the neuron is not actively sending a signal. The potential differences arises due to the unequal distribution of ions across the membrane, with more potassium ions inside the cell and more potassium ions outside the cell. So this creates a negative charge inside the cell relative to the outside, typically around minus 70 millivolts in neuron. So the correct answer here is the sodium ion and chlorine ion cannot pass, and it creates, and potassium ion can flow, and it creates a negative potential. And the potential difference, as I say, not actively refers to the electric difference across the membrane and not the cell. The potential differences arises due to the unequal distribution of ion, more potassium ion present inside the cell and more are present outside the cell. This creates a negative charge. Now moving to the next question. The standard potential of calomel electrode is the standard electrode potential of the calomel electrode is plus 0.26 volt, plus 9 volt, plus 0.62 volt and minus 0.9 volt. What is the calomel electrode? So the calomel electrode is basically a type of reference electrode used in the electrochemical measurement to establish a stable referential potential. So the calomel electrode is basically made of mercurous chloride, that is HgHgCl2, and it can be in contact with a solution of potassium chloride. It is usually represented as HgHcl2 KCl into M. So I will write that one. Hg Cl2 KCl into M saturated. The electrode reaction can be mentioned as HgCl2 just a minute. It is HgCl2 Hg2 Cl2 plus 2 electron, or it can be directly break. It can be given as 2Hg plus 2Cl minus. So this HgCl2 plus 2 electron. So here as is given, the calomel electrode is commonly used to establish the reference potential for measuring one electrode's potential. The calomel electrodes are electrode potential is known as to be the stable and reproducible, which makes it an ideal reference electrode for electrochemical measurement. In practical application, the calomel electrodes is often used in conjunction with working electrode to measure the potential difference between two electrodes. These potential differences can be used to calculate the concentration of substance in a solution or to determine the rate of a chemical reaction. So, as I said, the calomel electrode is basically the reference electrode commonly used for the electrochemical measurement. It consists of a mercury convert with a layer of mercurous chloride immersed in a solution of potassium chloride. The standard potential of calomel electrode is approximately 0 plus the standard potential is the calomel electrode is approximately plus 0.241 volt, though it can be very slightly dependent on the condition. The closest option here is provided as 0.268 volt. So the standard potential for calomel electrode is here. The correct option is plus 0.268 volt. Now moving to the next question. The concentration of K plus ion inside a human nerve cell is typically 5 millimole per decameter, 10 decameter cube, 10 millimole per decameter cube, 15 millimole per decameter cube, 150 millimole per decameter cube. So first we will discuss the role of K plus ions in inside a human nerve cell. K plus ions in the human nerve cell. So basically the potassium ion is basically involved in the formation of membrane potential of the nerve cells, which are commonly known as the membrane resting potential. The membrane potential exists in both neurons and glial cells, where more attention is often paid to the resting potential of the neuron. So basically the two sodium potassium pumps go through here. It is the exchange of the K plus and sodium usually done using a sodium potassium pump. The sodium potassium pump goes through a cycle of shape changes to help to maintain the negative membrane potential. In each cycle, 3 sodium ions exit the cell and 2 potassium ions enter the. So there is basically the here there is a pump exists in a human nerve cell that is known as NAK pump. This pump basically help to exchange the sodium and potassium. So because of that the 3 sodium is coming out from the interior of the nerve cell to the interior of the cell, interior of the cell to the exterior or extracellular, and 2K is transferred from the exterior to interior. Exterior to the interior. The concentration of K plus ion inside the human nerve cells is typically 150 millimole decameter or millimoles per decimeter. The options are 150 millimole decimeter. The concentration of the potassium ions inside the human nerve cell is represented as, or known as the intercellular potassium concentration. The intracellular potassium concentration is more compared to the intracellular sodium concentration. Now moving to the next question. The standard reduction potential of all the redox coupled are defined are relative to dash reference half cell. So there are 4 options. The standard reduction potential of all redox coupled are defined relative to dash reference half cell. So there are 4 options: Fe3 plus, Fe2 plus, H plus, H2, PT and AN. The standard reduction potential of all redox couples are defined relative to the hydrogen ion and hydrogen reference half cell. The standard reduction potential, also known as standard electrode potential, is a measure of the tendency of the species to gain electrons and undergo reduction under standard condition. It measured relative to the standard hydrogen electrode, which assigns as a potential of 0 volt at all temperature. The standard reduction potential is typically denoted by the symbol of E0. For example, the standard reduction potential for the half reaction, suppose Zn2 plus 2 electron, that is converted to Zn, is 0.76 volt, meaning under standard condition zinc ions tend to gain electrons and be reduced to the zinc metal with a potential of 0.76 volt relative to the standard hydrogen electrode. So the correct answer here is if the hydrogen H plus H2 electrode. Now moving to the next question. Enthalpy, the dash of the internal energy and dash of the pressure and volume of a thermodynamic system. So now here is the question which is purely relevant to depend on the classical thermodynamics. So enthalpy, there are 3 quantity. One is enthalpy, entropy and gives free energy. There are 3 main thermodynamic quantity. So first we will discuss what is enthalpy. So enthalpy is a measurement of energy in a thermodynamic system. The quantity of enthalpy equals to the total content of the heat in a system, equivalent to the system internal energy plus the product of volume and pressure. So enthalpy is basically suppose this is the reaction. So to state, the reaction state in this state and the products in this state. So a difference between the internal stages of these two, the internal energy difference between the internal energy of the two of the reactant and the product, it is known as the enthalpy. So basically enthalpy describes the internal energy that is required to generate a system and the amount of energy that is required to make a room for it, establishing its pressure and volume and displacing its environment. So suppose when a process is begin at a constant pressure, the evolved heat equals to the evolved heat which is either generated or absorbed equals to the change in enthalpy. So if I go by the study, so enthalpy is a thermodynamic quantity that represents the total heat content of a system at a constant pressure. It denoted by the symbol H. Enthalpy includes the internal energy of the system as well as the product of the pressure and volume of the system. So basically, suppose if a process begins as a constant volume and pressure, it either absorbs or generates certain amount of heat. So that so basically the enthalpy is amount of heat. So that is be produced. Suppose there is a piston which is kept at a constant pressure. So first, when we provide some heat, so first it will absorb, which increase the motion of the molecule present in this system, and because of that the amount of heat that is required to increases the motion of this particle known as the internal energy of the system. And after a certain amount for a reaction, when the piston started to go in the upward direction, this is the work done. So this is the basically the work done by this particular heating. So this part is the part which is help to enhance its motion, as well as help which occur due to the motion to the pistons, that is a change in the volume. So this total is known as the enthalpy. So in a mathematically it can be expressed as H, which is the enthalpy, U is the internal energy, P is the pressure of the volume, pressure is the volume, and V is the P is the pressure and V is the volume. Enthalpy particularly useful in a chemical thermodynamics. So basically it helps to describe the energy changes in a chemical reaction occurring at a constant pressure. So now comes to the question. So basically enthalpy, this is the sum of the internal energy and the product of the pressure and volume of a thermodynamical system. So I'll again describe the enthalpy one more time for you. Suppose this is a system and it is kept at a constant pressure. Now we providing some heat to the system. So what happened? First, the motion of the particle present inside the system has increased, which create a work at the piston and help to piston to go in a upward direction. So the amount of energy that required to get activated of this particle as well as the work done of this particle to get up the piston at after a certain height or enhances the volume is known as the combinedly known as the enthalpy of the system. Now moving to the next question. Multiplying a half reaction by any number does not change the value of enthalpy, entropy, bond energy, standard reduction, potential. So as I say, suppose there is a reaction, so the enthalpy is usually given by E. Enthalpy is usually calculated by the equation minus N F and E. So here the enthalpy calculation is dependent on the value of N, whereas the entropy is calculated as S equals to minus NF by T. Bond energy, because the half reaction is only involves the transfer of the electron from one system, the bond energy plays a role when new bonds are formed or bonds are broken. So in the change of like half reaction or electron transfer reaction, the role of bond energy is not very crucial, so ignore the term bond energy. And the fourth one is the standard reduction potential. It is a standardized term. It's determine the reduction potential of an electrode with in reference to other electrode. So this part is not very it's not dependent on the N. Suppose or the moles. So multiplying a half reaction by any number does not change the value of the standard reduction potential. Let's take a half reaction for the reduction of copper to copper metal. Suppose Cu2 plus 2 electron is converted to copper. The standard reduction potential for this half reaction is 0.34 volt. Now if we calculate the enthalpy value, so enthalpy value is comes around 1 into F means 96,856, the Faraday's constant, and the electrode potential is 0.34 volt. So 1 into 96,856 into 34. The value is coming around 32,93,104. Whereas in the case of 2 copper, when I multiplied the both half reaction by 2, so there is the conversion of 2, so that is coming around 65,000. So it's dependent on the number we are going to multiply on the number of the moles. Whereas in the case of delta S or the entropy, for the first reaction where the Cu2 plus, for this reaction the entropy value is coming around minus 1 into 98,650 6 divided by, we maintain the reaction at a 35. Suppose the reaction is occurred at 25 degrees centigrade, so it's coming around 325. Whereas if we double the reaction, its value is coming around 650. So the entropy is also dependent on the moles number. So we can say the enthalpy and the entropy does not require for these half cells. So we can say the enthalpy and the entropy doesn't make sense. The correct answer is the standard potential. So if we revise one more time from the first, so the first question is, read the following three statements. The activity of an ion in a very dilute solution close to infinity and can therefore be expressed in terms of ion concentration. However, the ion concentration is not equal to the ion activity for the solution having very high concentrations. In order to use the Nernst equation in such cases, experimental measurements must be conducted to obtain the true activity of the ion. There are four options: 1 and 2 and true, and while 3 is false. All the three statements are true. 1, 2, 3. The statement 2 and 3 are true, while statement 1 is false, and all the statements are false. These statements all pertain to the concept of ion activity in solution. In very dilute solution, the activity of an ion can be considered close to infinity, meaning that is essential as it behaves its Okay, so the correct answer of this question is all the statements are true, that is 1, 2, 3. Now moving to the next question. In a galvanic cell, reduction occurs. There are four options given: anode, cathode, depend on the electron used, and none of the above. And the correct option is option B, cathode. Now moving to the question number 3. Delta G equals to NFE, where delta G is the change in free energy and N is the number of moles and F is the Faraday's constant. So E is equal to what? There are four options: electron charge, current, voltage and charge density. So the correct option here is option C, voltage. Now moving to the next question. A reaction is spontaneous if delta G is dash and E is dash. So there are four options: positive and negative, positive and positive, negative and positive, and fourth option is negative and negative. So the correct option is negative and positive, that is option C. Now moving to the question number 5. When a nerve cell is at rest, so dash and dash cannot pass across the membrane of the axon, but dash can flow across the membrane from the cell interior to the exterior. As a result, a dash potential exits across the axon membrane. So there are four options: K ion, Cl ion, Na plus ion positive, Na plus ion, Cl ion, K plus ion positive, Na plus ion, K ion, C minus ion negative. So the correct option is option D, sodium ion and chlorine ion and potassium ion is negative. Now moving to the next question. The standard potential of the calomel electrode is 0.268 volt. Now option 7 is the concentration of K plus ion inside the human nerve cells. Typically there are four options: 5 millimole per decimeter cube, 10 millimole per decimeter cube, 15 millimole per decimeter cube and 150 millimole per decimeter cube. The correct option is option D, 150 millimole per decimeter cube. The question number 8. The standard reduction potential of all the redox couples are defined relative to the H plus or H2 ions. Now moving to the question number 9. Enthalpy, the dash of the internal energy and the dash of the pressure and volume of a thermodynamic system. So the correct answer is enthalpy, the sum of the internal energy and the product of the pressure and volume of a thermodynamic system. Now moving to the next question, that is the question number 10. Multiplying a half reaction by any number does not change a value of enthalpy, entropy, bond energy or standard reduction potential. The correct answer is the option number D, the standard reduction potential. Now moving to the, so it is the end of the week 3. Hope the questions are found to be informative for you, and we will be meet in the next class. Thank you all and all the best for your exam preparation.